Today, we're going to talk about one of the most underappreciated but absolutely essential pieces of tech in any modern aircraft, the avionics power supply. Now, I know, it sounds kind of simple, right? But designing one of these to survive the brutal environment inside an airplane, well, that is a whole other level of engineering. Let's get into it. You ever think about that? I mean, really think about it? The plane's flying through a massive storm. Lightning is cracking all around. And yet, inside that cockpit, every single screen, every light, every critical system, it's all rock solid. No flicker, no reboot, nothing. How is that possible? Well, the answer is inside a little box of electronics that's basically designed to survive an electrical apocalypse. And this is so important to understand. On an aircraft, stable power isn't just a convenience, it is literally the lifeline for the entire plane. A tiny glitch, just a momentary blip in the power, could be the difference between a perfectly normal flight and a catastrophic failure. We're not just talking about keeping the cabin lights on. We're talking about making sure every single system works flawlessly, every single second. Okay, so to really appreciate the challenge here, first you have to understand the environment. And believe me, the electrical grid on an airplane is one of the most hostile, unpredictable places you can imagine for electronics. Just think about the power in your house for a second. It's clean, it's stable, it's incredibly predictable. On a plane? No way. The power bus is a totally chaotic mess. You've got huge voltage swings, you've got sudden gaps where the power just disappears for a split second, and of course you've got these massive surges from things like a lightning strike. The power supply's job is to sit in the middle of all that chaos and protect everything else. So how in the world does it survive those power gaps we just talked about? Well, the magic trick is a concept called hold-up time. This is what lets the power supply keep pumping out perfect, stable electricity, even when its own input power completely vanishes for a moment. It's kind of like having a tiny, super-fast backup generator built right inside. And the amount of time it needs to hold up is incredibly specific. Engineers design for about 20 milliseconds. Now, I know, that sounds like nothing, right? But in the world of processors and flight computers, 20 milliseconds is an eternity. It is more than enough time to bridge any little gap on the power bus, making sure a sensitive flight computer never even knows there was a problem, and most importantly, doesn't have to reboot. So job one is surviving that hostile input. But its second job is just as hard. It has to deliver perfectly clean and stable power out to all the other avionics, no matter what they're doing. This brings us to two really important ideas: line and load regulation. Think of it like this. Line regulation is all about fighting that chaotic power coming in from the aircraft's grid. Load regulation is about handling the wild swinging demands of all the systems it's powering. Let me give you an example to show you why this is such a big deal. So imagine the pilot flips a switch and powers on a heavy-duty system, like the weather radar. This isn't like turning on a lamp at home. This is a huge, instantaneous demand for electricity. And the speed of this change is just mind-boggling. The electrical current being pulled can jump by 4 or 5 times, and it happens in less than a single microsecond. That is an almost vertical wall of demand hitting the power supply all at once. So if you suddenly suck that much power out of the system, what do you think happens to the voltage that's feeding everything else? The important stuff, like the navigation displays and the flight controls. The answer? Almost nothing. The power supply's reaction, what engineers call its transient response, is so fast and so powerful that the voltage barely even dips. It's kept to less than 5%. Any more of a dip than that, and you risk sensitive processors resetting, or worse, data getting corrupted mid-flight. The level of precision here is just staggering. So, on top of providing rock-solid voltage, the power supply also has to be quiet, stay cool, and be unbelievably strong. You see, all power supplies, just by their nature, create a little bit of electromagnetic noise or interference. In your house, who cares? But on a plane, that electrical noise could jam radios, interfere with navigation, or blind the radar. So it has to be ruthlessly, completely suppressed. And the scale of this is just crazy. For a really sensitive analog system, the maximum allowed noise is just 10 millivolts. To put that into perspective, a normal phone charger can easily be 10 times noisier than that. These avionics power supplies have to be electromagnetically silent. And then you have the problem of heat. These things have to be incredibly efficient. We're talking over 90%. Why does that matter so much? Because every single watt of energy that gets wasted turns directly into heat. And in the tight, cramped, often uncooled spaces of an avionics bay, even a tiny bit of extra heat can build up and cause a total failure. Now, believe it or not, so far we've only talked about the electrical problems. But these devices also have to survive a physical environment that is just plain brutal. The official standard for this stuff, called DO-160, it reads like a torture test. The power supply has to work perfectly, whether it's frozen solid or baking hot. It has to put up with constant bone-jarring vibration for hours on end, survive massive G-shocks from hard landings, and deal with the low-pressure atmosphere at 40,000 feet. So how do you make sure it's reliable under all that stress? Well, engineers use a really smart design philosophy called derating. Basically, they intentionally pick parts that are way stronger than they actually need to be. By only ever running them at, say, 50 to 70% of what they can truly handle, they build in this enormous safety margin. That's how you get a long, predictable, and incredibly reliable life out of it. So, when you pull all of these different pieces together, the electrical challenges, the physical abuse, you start to realize you're not looking at a simple component anymore. You're looking at a true masterpiece of multidisciplinary engineering. Seriously, to create one of these, you need a whole team of experts from totally different fields. You need somebody who understands control theory to keep it stable, power electronics experts for the efficiency, EMI engineers to make it quiet, thermal designers to keep it cool, and reliability engineers to make sure it absolutely, positively, never ever fails. And that's really what it all boils down to. The avionics power supply is the ultimate unsung hero. It just sits there, silently in the background, fighting off this constant storm of electrical chaos so that every other system, from the displays in the cockpit to the actual flight controls, can do its job and keep everybody safe. It kind of makes you wonder, doesn't it? What other pieces of invisible, incredibly over-engineered technology are out there, just silently making our modern world work? Something to think about. Thanks for joining me.